Good evening, ma'am. Am I audible to you?
Good evening, sir. Yes, sir. You are audible, sir.
Can I start now, ma'am?
Yes, sir.
Okay. Good evening, students. Today we are going to continue our discussion on the moving charges and magnetism. Okay. So last class we finished up to toroids. We finished up to toroids. So the concept of magnetic field into a toroidal solenoid or toroid. So that concept we have finished in our last class. So today we are going to discuss few more concepts. The first thing is, when you have a charge moving with some velocity, okay, when you have a charge moving with some velocity in a magnetic field, there is a force acting on, okay. So that concept is actually called Lorentz force actually. So force on a charge. Force on a charge Q moving with velocity V. Force on a charge Q moving with velocity V in a magnetic field. Magnetic field is represented by V. So force on a charge Q moving with velocity V in a magnetic field V. That force is actually given by vector F is equal to Q into V cross B. Okay, Q into V cross B. Where theta is the angle between here you can actually remove this cross product and then you can put sin theta QVB sin theta. So F equal to QVB sin theta, and theta is the angle between the movement or the motion of that charge, or theta is the angle between the velocity of the charge and the magnetic field B. Okay, so this is how you need to find out the force on a charge Q moving with some velocity V in a magnetic field. Okay, so here we are going to see some cases. Okay, so what are the cases? When will the force be 0? Okay, this force can be 0 in certain cases. The first thing is, when the force is 0, that means the Q should be equal to 0. This is the first scenario. That means that the particle is an uncharged particle. So when Q equal to 0, your force will be 0. Which means when you have uncharged particle moving with some velocity v in a magnetic field, then what happens is your force becomes 0. Okay. So this is the first case when the force is 0, and the second case is when the velocity is 0. In that case also you can have the force equal to 0. Velocity equal to 0 means the charged particle is stationary. So in that case you won't experience any force. Okay. The charge won't experience any force. So this is the second case. And in third case, when you have your theta equal to 0 degree. So sin 0 degree, your force will be 0. And likewise, you can also have the fourth condition, theta equal to 180 degree. So in that case also, you can have the force on the charged particle as 0. Okay. Right. Now, when your theta is 90 degree, okay, when your theta is 90 degree, then the force acting on the charged particle is a maximum one. So F max is equal to QV. Okay. F max is equal to QV. Yeah, because here you can see the sine theta value will be maximum when you have theta equal to 90 degree. Okay, that means when the charge is moving perpendicular to the field, the force acting on the charged particle is maximum. That is QV. Okay. Okay. So the next one important property is this force is called the magnetic Lorentz force actually. So this force is called the magnetic Lorentz force. This force is called magnetic Lorentz force, and when you take the dot product of this magnetic Lorentz force with the velocity of the charged particle, it will be 0. Okay, when you take the dot product of this magnetic Lorentz force with your velocity, then you will get 0. So why it is so? Because this force is actually perpendicular to both V and P. Okay, when you have a cross product between two vectors, the resulting vector will be perpendicular to both the vectors. It is the general concept in mathematical physics or mathematics. So here, this force is already perpendicular to this V. Perpendicular means angle 90 degree. So in dot product, when you have Fm dot V, you actually have cos theta here. So Fm into V cos theta. So since theta is 90 degree, the entire result will become 0 here. Fm dot V equal to 0. Okay. So this is how this equation is equal to 0. So that means Fm dot V means actually this is the work done or power. Okay, work done by magnetic field on the charge. So this relation is nothing but work done. Okay, work done by magnetic field on the charge is 0 because we have the formula for power in general P equal to F dot B. Okay, P equal to F dot B. So this is the general formula. So here you have Fm dot V, and that power or the work done is actually 0. Okay. So here the magnetic force and of course the acceleration due to this force is equal to F by M. Okay, the acceleration equal to F by M, because according to Newton's law, F equal to ma. So when the charge is accelerated, it is the ratio of the force and the mass. Okay. So here the acceleration is nothing but the change of direction only. The change of direction only because due to the magnetic force, only the direction of motion of the charge changes. So that's why you are having some acceleration there. Okay. So this acceleration equal to F by M. Okay. So this is how you need to work with the magnetic Lorentz force concept, and as you can see from this equation, okay, as you can see from this equation, F equal to Q into V cross B. So this implies that this force is actually perpendicular to both P and V. Okay, as I have told you earlier. to both B and B, this force is perpendicular. So this is an important result here. The force is perpendicular to both B and B. Okay. So then we will be discussing the concept of the motion of a charge projected perpendicular to magnetic field. This is the next concept which we are going to discuss now. Motion of a charge projected motion of a charge projected perpendicular to magnetic field. Okay. Motion of a charge projected perpendicular to magnetic field. That means the velocity and the magnetic field are perpendicular to each other. So in that case, what will happen? So in general, the force is actually QVB sin theta. So here theta equal to 90 degree. So the force is maximum. F max is equal to QVB. So what happens now is the charge moves on a circular path due to this force. Okay, the charge moves on a circular path due to this force. So that means when the charge is moving with the velocity perpendicular to the magnetic field, what will happen? The magnetic Lorentz force will cause the charged particle to move in a circular path. Okay, circular path perpendicular to the field. So when it is moving in a circular path, then this Lorentz force provides you the centripetal force actually. It provides the centripetal force. So F max equal to mv squared by r. That will be QVB equal to mv squared by r. Okay. So this is the expression for the centripetal force. mv squared by r is actually provided by QVB. And from this you can calculate the radius of the circular path. Okay, the radius of the circular path you can calculate here. How you can calculate? So from this expression, this v squared and this v will be cancelled. So r equal to mv by bq. R equal to mv by bq. So mv means momentum actually. So r equal to p divided by dq. This is one more relation. So these relations give you the radius of the circular path followed by the charged particle. So r equal to p by qb or pq. So the relation between momentum and kinetic energy is P equal to root of 2m into kinetic energy represented by Ek. Okay. So here R equal to, instead of P, what you can write 2m into Ek square root whole divided by Pq. Okay. And this is how you can calculate the radius of the circular path. And moreover, when the charged particle is moving in a potential difference capital V, okay, when the charged particle is moving in a potential difference capital V, then this kinetic energy is given by Q into capital V divided by V into Q. So this is actually the square root. Square root of 2m into q into capital V. So how did we arrive at this relation? Because the kinetic energy of a charged particle moving in a potential difference is Q into capital V. So you should not confuse this small v with this capital V, because here capital V is nothing but the potential difference through which the charge is accelerated. Okay. The potential difference through which the charge is accelerated. Right. So there are some other formulas as well. So we can learn that formula also here. What is the area of that circular path? Okay, because the charge moves in a circular path, so the area of the circle is given by A equal to pi r square, which means the area of that circular path is proportional to r square. Okay, so in the previous slide we have seen that this r is directly proportional to the square root of the kinetic energy. Okay, r is directly proportional to the square root of the kinetic energy. Here, this r is directly proportional to the square root of the kinetic energy, and from that relation we can r is directly proportional to square root of kinetic energy, which means r squared is proportional to kinetic energy. So this area, since it is proportional to r squared, this area is also proportional to kinetic energy. Okay. Moreover, this is proportional to the potential difference through which the charge is accelerated, because the kinetic energy we know very well of a charge moving in a potential difference is Q into capital V. So this area is proportional to potential difference also. Now, what is the time period of revolution of that charged particle, since it is moving in a circular path? Okay. So here, as I have already told you, when your charge is projected perpendicular to the magnetic field, the charge follows here, or the charge moves in a circular path. So that's why we are having all these equations. Charge moves in circular path. So now what we can do is we can find out the time period of revolution of that charged particle, t equal to 2 pi r by v. This v is the velocity. Okay. Time period is nothing but displacement by velocity. Here the displacement is the total circumference of the circle, that is 2 pi r by v. And we know very well that r equal to mv by bq. From our previous slide, r equal to mv by bq. We have it here. Okay, as you can see here, this r equal to mv by bq. From this slide, we can consider here. So r equal to mv by bq. And using this, you can calculate the time period. So t equal to 2 pi into mv by bq whole divided by v. So these v and v will be cancelled, and finally you will be getting the time period t equal to 2 pi m by bq. Okay, 2 pi m by bq is the time period. Okay, this is the time period of revolution of that charged particle. So this is the time period, and when you want to find out the frequency using the time period, the relation is t equal to 1 by f. That means the reciprocal of this time period, that will be dq by 2 pi m. This is the frequency, and from this you can calculate the angular frequency also. And what is the equation? Omega equal to 2 pi into F. Okay. This is actually T equal to 1 by F. So here time period T equal to 2 pi m by BQ. So the frequency is actually BQ by 2 pi m. Okay. T equal to 1 by F. That means here you should put 1 by this 2 pi m by BQ. So we should change here. So here it is 1 by F, 1 divided by T equal to 1 by F, 1 by F equal to 2 pi m by BQ. So that implies F equal to BQ by 2 pi m. Okay. So F equal to BQ by 2 pi m. From that, you can calculate the angular frequency. You can calculate the angular frequency using this relation. So omega equal to 2 pi into BQ by 2 pi m. Okay. The omega equation now is given by BQ by m. From here, omega equal to BQ by m. This is the angular frequency. So these are the formulas, much needed formulas to solve the numerical problems. In case when your charged particle moves perpendicular to the magnetic field, and we have one more formula for the kinetic energy of a charged particle. That thing also we can discuss now. The kinetic energy in general. Okay. The kinetic energy in general is given by P squared by 2m. So Ek equal to P squared by 2m. P is nothing but the momentum. Okay. P is nothing but the momentum. And of course, we know very well that P equal to dqr. Okay, P equal to dqr from this previous slide. I think here you have here this thing. Okay, here you can see R equal to P by BQ. From this equation, R equal to P by BQ. That means P equal to BQ into R. So from this, we can calculate the kinetic energy. So this is P equal to PQR. So P squared Q squared R squared by 2m. Okay. This is the expression for kinetic energy of a charged particle moving perpendicular to the magnetic field. Okay, so these are the important formulas which you should keep in mind while solving the numerical problem. Then we shall discuss the concept of cyclotron. Okay, cyclotron we shall discuss now. What is meant by cyclotron? Can anyone tell me? What is meant by cyclotron? Can anyone tell me? Does anyone have any idea about cyclotron?
So,
Yes,
is it some kind of particle accelerator, sir?
absolutely right. So cyclotron is a device used to accelerate ions actually. Okay. So charged particles can be accelerated by cyclotron, and here you are having magnetic field applied perpendicular to the velocity of the ion. Okay. So in that case, the ion travels in a circular path, and all the formula related to the charged particle moving perpendicular to the field. So all the formula are applicable here also for cyclotron. Okay, because in a cyclotron actually the charged particle moves in a circular path, and you can find out the different parameters like radius of the circular path, and the time period of revolution of the charged particle. All these formula are applicable here also. So using this you can find out the different values of time period, frequency, or kinetic energy of the charged particle in the cyclotron. You can find out using the formula which we have discussed earlier. Okay, right. Then the next thing is, so far we have discussed the concept of a charged particle moving perpendicular to the magnetic field, but now we shall consider the charged particle projected at an angle, at an acute angle. Okay, so motion of charged particle moving at some acute angles. Moving at some acute angles to your magnetic field. Instead of 90 degree, it is some acute angle. So in this case, what will happen? The charged particle follows a helical path. Okay, the charged particle follows a helical path. So here the velocity can be resolved into different components, since the velocity is at a particular angle. Okay, so here you can see this is the diagram. You have your velocity here. So this is your y-axis, and this is your x-axis. X-axis you have magnetic field, and then your velocity is having some angle theta here. Okay, then you will be having the parallel component as v parallel equal to v cos theta, and the perpendicular component v perpendicular equal to v sin theta here. So when you have your charged particle moving at this kind of acute angle, then your charged particle follows a helical path. And how does a helical path look like? So it looks like this. The charged particle follows a helical path. Okay, it looks like a solenoid actually. The charged particle follows a helical path like this. So here you are having some different formula. R equal to, or the radius of this helical path. In general, for helical path, it is actually different. So In the direction of B, it has a linear motion, and perpendicular to B, it has a circular motion. So both linear and circular motion is possible only in this helical motion. So that's why the charged particle follows a helical motion. I think you are getting my point, because due to the parallel component of this velocity, the charged particle moves linearly. Okay, but due to the sin theta component, the sin theta component is perpendicular to this magnetic field, so it moves in a circular path. So the combination of linear path and the circular path gives rise to helical motion here. Okay, how this helical motion is possible? Because you have both linear motion due to parallel component plus circular motion due to perpendicular component. So linear motion is due to B parallel. Okay, this is due to B parallel. Circular motion is due to V perpendicular. So the combination of this linear motion and circular motion leads to the helical motion. So these are the important formula here, and this is how you need to apply the formulas when you are asked to solve the numerical problems related to this. And the next concept is, when you have both electric field and magnetic field, and your charged particle is moving with some velocity. Okay. So when you have both electric field is represented by vector E, magnetic field is represented by vector B. Okay. So both fields are there now, and when your charged particle is moving with velocity v, in the presence of both these fields, then the force acting on the charged particle is given by Q into V plus E cross B. Okay. Sorry, E plus V cross B is. So the force acting on this is given by F equal to Q into E plus B cross B. Okay. So it's very simple. When you have a charge in an electric field, the force experienced is F equal to QE. When you have the charge moving with velocity V in a magnetic field, the force experienced is F equal to Q into V cross B. So when you have both electric field and magnetic field, then the total force is given by F equal to Q into E plus V cross B. Okay. This is very simple, and using this equation you can find out the force. Then the next concept is force on a current carrying conductor placed in a magnetic field. So the next concept is force on current carrying conductor kept in a magnetic field. Kept in a magnetic field. So F equal to IL cross B. Okay. F equal to IL cross B, where the length of the conductor is L and the magnetic field is B. So when you have a conductor of length L carrying a current I and it is kept in a magnetic field B, then the force on the current carrying conductor placed in the magnetic field is given by F equal to IL cross B. Okay. This is the expression you need to understand and you need to apply for different cases. Okay. Then we have a magnetic force between two long parallel current carrying conductors or wires. The next concept is magnetic force between two long parallel current carrying wires. Two long parallel current carrying wires. So for this, you need to draw a diagram. So here you are having two long conductors and both separated by a distance d. Okay, both separated by a distance d. So you are having current I1 and here I2. Okay, on conductor 1 the current is I1, conductor 2 the current is I2. Then what is the force acting between these two conductors? That force is given by F equal to mu naught I1 I2 divided by 2 pi into d. Okay, 2 pi into d. So this is the expression for force acting between the two conductors. That two conductors are separated by distance d. Okay. And another important thing to note here is here the currents in both the wires are in the same direction. In that case, the wires are attracted each other. Okay. So actually the concept is when both conductors carry current, when both conductors or both wires carry current in same direction, they attract each other. They attract each other. But when both conductors carry current in opposite direction like this, okay, so here you have one wire and here you have another wire separated by the same distance d. So here d, but now the currents are in opposite direction. So I1 is like this and I2 is, in that case these two conductors experience repulsive force. Okay, repulsive force. So when the current carrying conductors carry current in opposite direction, they repel each other with the same amount of force mu naught I1 I2 by 2 pi into d. Okay. So this is the concept of magnetic force between two long current carrying wires. Okay. Then we will move on to the next concept. So the next concept is current carrying loop as a magnetic dipole. So when you have a loop carrying current, so that current carrying loop actually acts as a magnetic dipole. So current carrying loop as a magnetic dipole. So a current carrying loop actually acts like a magnetic dipole having magnetic moment capital M equal to I into A, where I is the current flowing through the current carrying loop and A is the area of the loop. When you have n number of turns, then this equation is modified as M equal to NIA. Okay, so this is the expression for the magnetic moment. And the next concept is torque on a magnetic dipole in a magnetic field. Torque on a magnetic dipole kept in a magnetic field is the next concept. So here torque on a magnetic dipole. Kept in an external magnetic field. So when you have a magnetic dipole and it is kept in an external magnetic field, then what is the expression for torque? Okay. For that, I will be drawing one diagram now. So here you have a north pole of a magnet, and here you have the south pole of the magnet. This is the north pole and this is the south pole of the magnet. I am just considering this. Okay, so this is the north pole of the magnet. This is the south pole of the magnet, and you have your coil like this, or magnetic dipole, or when a coil carrying current, it is actually a magnetic dipole. Just now we have discussed, right? Current carrying loop as a magnetic dipole. So similarly here, this current carrying loop is kept like this. We have magnetic field in this direction. Okay, we have magnetic field like this. So this loop, current carrying loop, is kept in this magnetic external magnetic field. Then what is the expression for the torque acting on this magnetic dipole? Torque means the magnetic dipole actually rotates in the external magnetic field. The expression for torque is given by tau equal to BIA cos theta, which means B is the magnetic field due to the external magnet. So this north pole and south pole will contribute to a magnetic field B, and I is the current flowing through the loop, A is the area of the loop, and theta is the angle between the loop and the external magnetic field. Okay, so this concept is similar to the concept of torque on an electric dipole kept in an external electric field. Same concept we are applying here. Okay, so tau equal to BIA cos theta, and we know very well here M equal to IA. Okay, here M equal to IA we know very well. So what we can do is this torque is equal to B into IA means M. So BM cos theta. So this cos theta can also be represented as sine of 90 minus theta. Okay, So tau equal to Bm sin of 90 minus theta. So instead of cos theta, you can put sin alpha like that. So tau equal to Bm cos theta or BIA cos theta. When you have n number of terms, so you can also substitute the another formula is tau equal to m cross b. When you have alpha as the angle, okay. So here theta is the angle between this coil and magnetic field, and alpha is the angle between the normal to the plane of the loop and the magnetic field. Okay, here you can take alpha. Alpha is the angle between normal to the plane of the loop. Normal to the plane of the loop and magnetic field. So in that case, tau equal to BIA sin alpha or tau equal to m into b sin alpha. So tau equal to m cross b. Okay, tau equal to m cross b.